Hello everyone, how are you? Welcome to Hydraulic Engineering. This lecture is recorded for the 20th of January 2015, pre-recorded. This is Tuesday. The homework assignment that's due today should be submitted to me by 4 p.m. Remember, as I mentioned previously, I'm on a teleconference today, so please don't knock on the door. Just slide your assignment under my door if you're turning it in while I'm still doing that, but I'll have about an hour. From 3 to 4, I'll be available for questions if there's just some final uncertainty that you want to check on before you submit the assignment. On Thursday, so our next class meeting, we will have a quiz, and I realize that some of you will be away at the Winter Technical Conference. You'll be able to make that up during my office hours. We'll work it out, but I just wanted to give you a heads up that the material you just submitted for the homework will be quizzed on Thursday. And finally, your next homework assignment, homework number 2, you can see the problems listed there. That's due on Tuesday the 27th in class, back to our normal, at the beginning of class, homework submission schedule. Today we're going to continue talking about pipe friction and the implications that pipe friction has on pipe sizing and design. So we're in chapter 8 of the textbook now. First we're going to go over the Colebrook equation, which is a really detailed and accurate equation for finding the friction factor F. Then we'll talk about the Jain equation, which is an explicit equation that's a little bit easier to use than Colebrook, though sometimes not applicable and sometimes not as accurate. And finally, we've got a couple of examples related to pipe diameter design. The majority of this lecture was recorded last semester, although I had to edit in something at the end. So there are a couple of times where I'm working on the board and I am emailing you a PDF and also attaching it to MU Online so that you can see what I've written on the board during those times that I'm talking through it on the screen.
This is one of the ways to find the F value when you have a situation that you know the Reynolds number and you have to use the relative roughness, which is the material type roughness, K sub S, relative to the pipe diameter, and then take that across to the second vertical axis to find the F value. Right. So let's say, for example, because the curve makes it a little bit tricky, let's say that you had 1 times 10 to the 5th as your Reynolds number, and let's say that the relative roughness was 0.004. So rather than just following this line straight over and intercepting 10 to the 5th, what you do is you follow the curve, and where the curve goes upwards and intercepts that 10 to the 5th is then where you'd go over to the left axis and find the F value. So sometimes you'll be between the lines, right? What if your relative roughness was 0.003? Well, there's no line for that. What you do is you find evenly spaced between 0.004 and 0.002. So find some midpoint between them and continue to be between those lines until you're at the intercept. And so the intercept between those two lines, and then go over. So you follow the curve, or you use the curve as guidelines of where you should be. Other questions about the Moody diagram? All right. So how rough is the pipe? How rough is the pipe depends on a variety of factors. Remember that it depends on the material that you're using. So a glass pipe is going to be much smoother than a cast iron pipe because of the material that's being used. The F value, the roughness, depends on the diameter, it depends on the flow conditions, and so in the many different ways that there are to estimate pipe roughness, the Darcy-Weisbach equation is the most accurate because it accounts for the most variables, but it's also the most challenging to use because the F value changes based on flow conditions. In the Hayes and Williams, which you took a look at last semester with that pipe rack lab, the C values in theory should be constant over the range of flow rates. And the same is true of a Manning's equation N value, that the roughness is constant. It does not depend on flow conditions. But the F value, which is the most accurate of all the roughness methods and the one we're going to be using the most in closed conduit flow, the F value is dependent on flow conditions, and so that's why it makes it a little bit challenging for us to find what is the F, is because it's always changing with the flow rate. So as we saw from the Moody diagram, it's easy to find the F value if you're in the rare laminar flow conditions. It's just 64 divided by the Reynolds number. But otherwise, in any other Reynolds number above that, the Colebrook equation will always be valid and relatively accurate. It's the most accurate way of finding the F value. And I'll be introducing 3 different equations today for finding the F value. Colebrook is the most difficult of those 3 methods, but it's valid over the longest range of flow conditions, and it's the most accurate. So it's an investment. What makes it hard to solve is the fact that it's an implicit equation. In an implicit equation, you'll see that we're solving for F, but F is in both the left-hand side and the right-hand side of the equation. And I've had students try and rearrange it and do algebra and isolate the F so that it's only on one side of the equation, but it doesn't work out. You'll be doing that all day long. Those F values are on both sides of the equation. And so the way that you solve an implicit equation is either trial and error or on Excel, which is the method that we're going to be using today, or your calculator can do it. I assume that many of you are using the Casio calculators that were forced on you at an early age here in your program. I prefer HP calculators. Dr. Pearson and I don't see eye to eye when it comes to calculators, but the Casio calculators can solve this equation if you know how to put it in, but it takes about 30 seconds. It'll be thinking and thinking. That little process in there is just about heating up and almost on the verge of melting. But you can find the F value if you can find a way to type it in, which is the challenging thing on a little calculator like Casio. We'll use the Excel method, and anytime you have an exam and I ask you to solve the Colebrook equation, you'll be able to use Excel. Our exams, you'll have access to Excel for them. So that's the demonstration we're going to do today. Now, we've talked about equivalent sand roughness, and there was a table in a previous lecture, and you needed to find the equivalent sand roughness for the homework assignment. One of the problems, I addressed that in the email that I sent you. Here's another table that just shows the equivalent sand roughness for a variety of different materials. And we're going to be using them today to find the F value. What we'll do in the trial and error approach is we'll guess some F value and find out, well, what's the left-hand side of the equation with that guess F value. And we'll put in all the other things that we know. We'll put in the pipe diameter that we know. We'll put in the relative roughness, the equivalent sand roughness that's based on the material. And then we'll try and find out what is the right-hand side of the equation for that same guess F value that we used on the left-hand side. And we'll keep changing the F value until the left-hand side of the equation and the right-hand side of the equation match each other. So here's our first attempt at trying to solve the Colebrook equation. What if we have a 136 millimeter diameter pipe and we want to find what's the roughness value, the F. It's galvanized iron, which according to the information we have has an equivalent sand roughness K sub S of 0.15 millimeters. And the flow rate going through is 200 liters per second. Now obviously we're going to have to first start off by finding what's the Reynolds number, because Reynolds number is one of the variables that goes into the Colebrook equation. Okay, so we have diameter is equal to 0.136 meters. K sub S is 0.15 millimeters. The area of the pipe, based on that diameter, pi d squared divided by 4. The cross-sectional area is 0.01453 meters squared. And we can find the flow rate by dividing by 1,000, because there's 1,000 liters in a cubic meter. That gives us 0.2 cubic meters per second. So if Q equals VA, the continuity equation, then of course the velocity of flow through the pipe, V, will be Q divided by A. So the flow rate that's going through that pipe is 0.2 cubic meters per second. And the cross-sectional area of the pipe, which is based on the diameter, is 0.01453 square meters. That means that the velocity of water that's flowing through the pipe is 13.77 meters per second. So that's the speed of the water going through the pipe. And that's really fast, 13 meters per second. That's extraordinarily fast. So we want to find out what's the friction factor. We have to find the Reynolds number that goes along with that flow velocity. And this is water that's flowing through the pipe. We'll consider it's just ordinary water with the ordinary kinematic viscosity of 1 times 10 to the negative 6th meters squared per second. So we'll find the Reynolds number for these conditions are the velocity, which is 13.77 meters per second, times the diameter, 0.136 meters, and the kinematic viscosity, 1 times 10 to the minus 6th meters squared per second. And we get from that the Reynolds number is 1,872,413. That's the Reynolds number that we're going to use in the Colebrook equation. So if we were going to do this by hand, and you always can do it by hand, you know, just the fact that you don't have Excel handy or you didn't figure out how to program it into your calculator doesn't mean all is lost. You can do the left-hand side, right-hand side thing. So, you know, if we have 1 divided by the square root of f is the so-called left-hand side of the equation, and the right-hand side of the equation is negative 2 log k sub s divided by 3.7d plus 2.51 divided by the Reynolds number square root of f. That's the right-hand side of the equation. And by the way, there's a similar version of the Colebrook equation that has it in terms of natural log, ln. So don't be thrown off if you see in a reference somewhere that they've got the Colebrook equation written in terms of natural log rather than base 10 log. It doesn't matter. You'll get the same result. So if we wanted to just guess, let's say, you know, what is the actual f value here? What if we said let f equals 0.02 is our guess. So what's the left-hand side if we do that? You know, if we have the square root of f and 1 over the square root of f, then the left-hand side is equal to 7.071. And the right-hand side, if we put in the k sub s that we know, and the diameter that we know, and this Reynolds number we just calculated, and then this guess f value, then the right-hand side would be equal to 7.024. And since those two don't equal each other, like the equation says they should, then that means this guess f value isn't right. And so we need to come up with a different guess f value. If we guessed, for example, well, what if it is 0.01 for the f value? Then that would give us 10 for the left-hand side and 7.013. So we were better off with this other guess. We're getting further away. So there's no sense to do this by hand if we've got Excel available. Excel can automate the trial and error quite nicely for us. So if you haven't already, start up Excel. We'll start with a blank workbook. All right, so what we want to do is put in the Colebrook equation, and I'm going to actually open an existing spreadsheet I have because it's got the Colebrook equation entered in, and I can have it in front of me and you can see it. Assuming it opens. There it is. All right. I'm going to erase all of this so you can see the equations we're going to type in. So what you need to have up here is a k sub s value that we're going to reference, a diameter, and the Reynolds number. You don't need to type in the equation necessarily. You'll have that on paper and you've got that on the screen. But type in these three values because we're going to be referencing back to them. You don't have to have the units. I just type the units there so that I remember what it is that I'm working with. And when you're working really quickly, even though it's K sub s, you don't have to bother to put in the subscripts. You know, maybe in a homework assignment, but here in an in-class example, it's not critical that we get everything subscripted correctly. No, not that I'm aware of. All right. So what we're going to do is we're going to start off with some guess f value. And maybe at the extreme low end, 0.008 would be a really low f value. And we're going to just work our way up in increments of 1. The next one we'll do is 0.009. And then we'll go over the entire range of possible f values and try and find out where does the left-hand side and the right-hand side match up. So the left-hand side is just going to be equals 1 divided by the square root, SQRT, of this guess f value. All right? So that would be the left-hand side. The right-hand side is going to be a little bit more tricky to type in, but we'll go slow. Everybody feeling good about that left-hand side? All right, well, let's do the right-hand side. So equals -2 times the log of K sub s. Now, instead of typing in the K sub s value, I'm going to reference the cell up here. And that way, I could change the K sub s value if I wanted to. So I'm going to click on the location of the number, and I'm going to push F4 because, oh, now I've done something tricky here. Let me show you. You can actually rename cells. Like you see over here, this cell name, it's D10. See how right here it says the name of this cell is D10? Well, the name of this cell, B3, I've actually named that cell K sub s. You can rename cells if you want. That way, when I'm doing my formula, I don't have to do B3 and then anchor it. I can just type in KS, and it'll know that I mean this cell right here. Little shortcut. Well, let's say that I want this to be called, well, I've already done it. You just type over here in this corner. Let me erase it, and then I'll put it in again. So if I delete its special name, tacos. Okay, what if we just call it its normal B3 is its name? And it doesn't want me to rename it. Okay, so let's say that we want to rename cell D3. It's called D3 right now, but what if we wanted to rename it snow? You just go in there and type snow, enter. And so now if I'm typing a formula and I want to use the value that's in here, I could just type the word snow in my formula. All right. Okay, so when I do my right-hand side, okay, so we'll start over. It is equals -2 times the log of K sub s. So I'm just going to type KS, and it knows what I mean. And I don't have to anchor it because there's no other cell in the spreadsheet that's called KS. Divided by 3.7 times D. I could have just typed D, but I chose to select the cell instead. All right, close that parentheses, plus 2.51 divided by the Reynolds number, oh, parentheses, Reynolds number times the square root of this F, which was in cell A10. Close parentheses, another one, and another one. There we go, finally done. I'll leave that up for a second because it can be tricky sometimes with all the parentheses to know if you've got it right. do this. I'll come back to it, don't worry. Does that make it bigger? Sort of, yeah. So when you press enter, you should get 7.01 as the result of the right-hand side. Okay? Let me circulate around and make sure everybody's got that. I'll help you troubleshoot the spreadsheet if you don't. An even better way of doing these formulas, it'll save you a couple of keystrokes. Okay, I'm going to type it in again manually for this next one. Instead of, what I could do is I could just drag it down, you know, just drag it down like that, and it changes the formula so that it stays on these. I want it to stay on these because these three things aren't changing with the different guess F value, but it's looking at the next row. That's the effect of dragging it down one cell. Rather than just doing that, I'll type it in manually. So the left-hand side was equals 1 divided by the square root of the F, and enter. Yeah. And the right-hand side equal -2 times the log of K sub S. So I'll click where the K sub S is. Now, if you didn't rename it to K sub S, if you just clicked on the cell B3, then you'd need to anchor it. You know those dollar signs? The dollar signs make sure that when you drag it down, it continues to look in the same place. So you can type in the dollar signs manually, or you can push the F4 button on your keyboard, and then it'll anchor that automatically. The F4 will put in those dollar signs before both the number and the letter. Okay, so K sub S divided by 3.7 divided by D. And that's a little tricky thing that I do to avoid too many parentheses, is I put in like the double divide thing. So having K sub S divided by 3.7 divided by D is the same as K sub S divided by 3.7 times D and then another parentheses. So it's just, you know, both 3.7 and D are in the denominator, so I sometimes will make that shortcut. So this one would be 2.51 divided by the Reynolds number divided by the square root of this F value. So fewer parentheses to keep track of, but sometimes people are a little bit confused by this double divide thing. But it works. Okay, so now let's say that we're going to do this. So I want it to continue its numbering automatically all the way down through 0.38. That's maybe at the upper range of what we'd see for an F value. So you can just, once you have two numbers typed in, down in the corner, you can click and then drag it, and it will automatically continue to increment each number in the according to the spacing that was between the first two. And then for the left-hand side, you can click and drag if you want, or you can just double-click on that corner and it'll fill them all in. Okay, and the same thing's true over here. If you double-click, it'll fill them all in, all the way down. And then the difference here is we're looking for the two sides to be equal. So the left-hand side minus the right-hand side, and I know that I have the correct guess F value when the difference is equal to 0. So the answer is somewhere between here and here. Right? So that would tell me, oh, maybe this 0.21 is a little bit too high. So what if I made it 0.0205? That gets me closer, but still a little too high, so I'll make it 4. Getting better. What about 2? And that's too much. 3. That's nice. That's a good F value. So here we'd now say this is the answer. All right. So let me pause this again, and I'll answer any formula questions you might have. This is a good method to have in our back pocket, but we can do better. We're going to use goal seek. And so goal seek, what it does is we have the same equation as before. We have the same case of S. By the way, start a new tab at the bottom of your spreadsheet and save it. You should save this file so that during your homework you can come back and use this. Maybe it'll be helpful for you. And so since you're using these tablets, you can save on your V drive and come back to it, the network drive, or use a plug-in USB jump drive, something like that. If you save it onto the local C drive on the laptop, then that won't be any use to you because that laptop's going to be locked up. So when you go to save the file, save as, then the location on the computer should be the V, right? Or if you have a jump drive. Okay. So what we're going to do with the trial and error approach that's automated with goal-seek is, let's say that we have a guess value. Our initial guess value was 0.008, right? Our left-hand side will have the same formula, equals 1 divided by the square root of f. Okay. The right-hand side, same formula. And it's good that you get practice typing this formula in because you need to get so that you can look at an equation and it's no problem to type it in, that it causes no concern or frustration for you. Equals -2 times the log of k sub s divided by 3.7 divided by d plus 2.51 divided by the Reynolds number divided by the f value. This is the guess f value that we're working with, square root of the f value. All right. So you type it in, and then the difference is simply going to be left-hand side minus the right-hand side. So it's the same thing as you had before, but we're just going to use a different approach.
I have a question. When I try to name this cell, like case of S, it keeps referencing the cell on the other sheet. Does it always do that?
It may use one. If you name a cell, it might be that in the entire file, it's that one cell, regardless of its worksheet location. Yeah. Yeah.
You know why won't we click on Excel anymore?
Pardon me? The computer's misbehaving?
I don't know what's wrong with it. They'll let you do that, but it won't let you click on it.
I can't explain it. You may have to just work with someone else if the computer's being weird. All right. So get it typed in again, and maybe you've used goal-seek before. Go to Data, this tab at the top, Data, and What If Analysis, goal-seek. And our goal, obviously, is that we want the difference to be 0. When the difference is 0, that means that the left-hand side and the right-hand side are the same. It means that we've found the correct f value if those two things are the same. So our goal is this difference to be equal to 0. And what it has permission to change in order to try to make that happen is this guess f value. Once we click OK, it's going to keep playing around changing the f value until it finds some combination, some f value that the left-hand side and the right-hand side are equal, meaning that the difference will be 0. And it's done that. Okay. So it goes through and it tries a bunch of different values and it finishes, okay, we'll keep this. And so then it tells us what the f value should be. And that matches what we had before. We said the answer was 0.0203. And goal-seek found it. Here's the precision that goal-seek found it to. More precision than we need. Okay? So I'll circulate around while you play around with goal-seek. If you have this out to a lot of digits, sometimes it won't get all the way to perfect 0. So for the level of precision we need here, goal-seek is fine, but sometimes I'm just giving you some additional information here. Solver is more powerful. It's a way of you don't have to know what number you're going for. In this instance, we knew that we were trying to make the left-hand side and the right-hand side such that the difference was 0. Well, there's something called solver that's a little bit like goal-seek, but it has more precision and more flexibility. So it's not available right now. I need to install it on here, I guess. You'd go to Options, Add-ins, Solver add-in. Okay, I want to manage the Oh, solver. Okay, they just must have moved it somewhere. Data. Oh, okay, yeah, there it is. Solver. So here I want this to be equal to 0, is value of 0, by changing the guess f value. And the nice thing about solver is that you can tell it how close it has to be. In other words, you can tell it what the convergence criteria need to be. So this, I can adjust how much precision I'm saying should finish it. And you can see right now the convergence criteria, it looked like it was 3 zeros when it comes to goal seek, but here in solver I've got it set to a lot more precision than that so that I can have it work a little bit more and it'll get it closer. Now it found the perfect f value that makes those two really equal. There are some situations in hydrology where you have to use solver because the goal seek isn't good enough. So, File, Options, Add-ins, Manage Excel add-ins, and then turn on the solver add-in once you get to there. But this semester you won't necessarily have to use solver. Goal seek's good enough. It's really bizarre. I've got it written down somewhere, but not with me. Is it logged in as someone else?
Yeah, won't let me log on.
Not by yourself? Yeah, I don't think I've got it here with me, unfortunately. Sorry about that. Okay. So that basically tells you how to solve the Colebrook equation. That's a lot of work, right? That's a lot of work. I mean, it's fun work, luckily, but still, it is work. So here is another approach. Now, the equation we were just looking at, the Colebrook equation, is implicit. What does implicit mean? That's right. So the variable, the unknown, is on both sides of the equation. What about this one? Is this one implicit or explicit? Yeah, since Colebrook is implicit, it's a lot of work, but this Jain equation, which is on screen here, is not implicit, it's explicit. And the limitation, though, is that it's not valid over the same range that the Colebrook is. Remember, the Colebrook equation is always valid, but the Jain equation should only be used when the ratio of k sub s to d is between 10 to the minus 6th and 10 to the minus 2. So there's only a certain range of relative roughness it'll work for. And the other thing is it's only valid over a narrower range of Reynolds numbers. So you have to be above 5,000 and less than 10 to the 8th for the Jain equation to be valid. This semester, you can use the Jain equation unless I specifically tell you to use Colebrook. I might give you a quiz or an exam question where I want to see if you can do Colebrook equation, but unless I tell you you have to use Colebrook, you can use this simpler Jain approach. So let's have an example of trying to use this Colebrook, the Jain equation. For the same conditions from the previous example, we found what the f value was with Colebrook, right? According to Colebrook, our f value is, we'll see how different they are. It'll be an interesting comparison. Okay, Colebrook said f value is 0.2027. 2027. And that's the hard way. Let's find out what f value we get by using the easy way. Okay? So Jain equation, we have f is equal to 1.325 divided by logarithm of 0.15 millimeters, which is the k sub s, divided by 3.7 times the diameter. Remember, we have to have the diameter in the same units as the relative roughness, meaning millimeter. Otherwise, that won't work out. Plus 5.74 divided by the Reynolds number, which was 1,872,413 to the 0.9 power. Okay, try that with your calculator. And then we take all that squared. So if you will, solve that with your calculator. And what I sometimes recommend is break it up into steps. You know, find out what is this quantity, and then find out what is this quantity. And it makes it a little bit easier to double check your work as well. So the F value according to the Jain equation, 1.325 divided by the logarithm of two different things. There's two terms in here. And what happens if you've got a really big Reynolds number in this? Like, what if the flow velocities are very high? Big Reynolds number is going to mean that of these two terms, this second term becomes insignificant. And so with a really high flow rate, a really high flow velocity, in other words, because remember, Reynolds number corresponds to velocity. And since RE is velocity diameter divided by kinematic viscosity, if you have big V, that goes to big Reynolds number. And if you've got a big Reynolds number in this Jain equation, then the second term goes to 0. So what that means is that at really high velocities, the F value is going to depend almost entirely on the K sub s to d, the relative roughness. And we're getting close to that range here. You look of the two terms, the bigger number of these two terms that we're going to be adding together comes from the first of the two terms, which is the K sub s to d term, rather than the Reynolds number term. So the F value, back to the main point of the example, is how close are these two things? Well, we're right in the range that we should be. We're in the range of values where the Jain equation is going to be accurate. We're in the correct Reynolds number range. We're in the correct K sub s to d acceptability criteria. So it works out to match really nicely. You know, there wouldn't be any problem with using the Jain equation for this example. Any questions on the Jain equation? And as I mentioned to you already, that the Jain equation is your go-to way of calculating F, unless I specifically ask you to do Colebrook. The text mentions that there's another approach for calculating the F value, and it only works if the Reynolds number is up to 100,000. It's the Blasius equation. And I don't remember, you may have an example or a homework problem where you have to just compare the different values, and so they ask you to find the Reynolds or the Blasius equation, but simple enough that we won't work an example with the Blasius equation. It's just dependent entirely on the Reynolds number for low Reynolds number values. All right. So for the rest of class today, what we're going to be talking about is how to make a pipe sizing decision when you know the head loss that there's going to be and when you know the flow rate that needs to be carried through a pipe. So when would you know that? Let's say, for instance, that you know that your water tank is going to be located on a certain place. You know, you've got a hill, here's a house. Okay, you know that your water tank's going to be up on the hill, and so the water surface elevation is going to be known if this is the origin of the water. and the water is flowing through a pipe, and it's going to go up to somebody's house, and here's their room, and there's a faucet. And so water is dripping out of that faucet there. And so you know, like the Z2, and this is Z1. So the elevations are known in a case like that, and the pressures are known. The pressure inside the tank, it's open to the atmosphere, so the pressure would be 0 there. When the water comes out of the faucet, the pressure is going to be 0 there. So the only thing that is going to really, in this case of an open faucet and an open tank, the only thing that is going to drive the head loss is going to be the difference in elevation. It wouldn't necessarily have to be an open faucet there. You could say, what if you have a pipe, and that at a certain pipe here you want to have P2? So we could just as easily say we want there to be a certain pressure. But because head loss is defined as the difference in energy between two locations, between 1 and 2, there's a certain amount of energy that's being lost. And we can use this formula to calculate it. It's just rearranging the energy equation to solve for H sub f. The velocity term, of course, goes into the energy equation, but it's a common practice to neglect the velocity head term because relatively little energy exists as velocity head compared to elevation and pressure head. Unless the water is moving very, very fast, it doesn't account for much of the energy. So let's say that because you know the orientation of where things are, you know how much head loss there's going to be, and you know how much water is required at the destination. It may be a residential house that requires 5 gallons per minute. It may be a fire hydrant that requires much more than that for firefighting purposes. You know how much water is needed, in other words. And the unknown is how big and what material should the pipe be? What diameter should the conduit be, and what's the material type that should be designed to match the conditions? And of course, the difference between design and analysis is that in analysis, all you're doing is you're finding out for an existing system, how does it behave? But in design, you are the author of the system. You're making a decision about how big it needs to be in order to match some required specification. So here the required specification would be, given the elevations involved and given the required pressure that's needed at a certain location, how big should the pipe be to deliver a certain flow rate? You'll be in the design seat. The Darcy-Weisbach equation can be rearranged to solve in terms of diameter. And let's go through that just briefly, what that looks like when we rearrange the Darcy-Weisbach equation. Any questions so far before we go through this very brief equation? Okay. We know that H sub f is FL v squared divided by d2g. Now there's a reason why I'm stepping through this instead of just putting it on the screen, because there's a substitution I'm about to make that's a really important substitution. And some of you may forget about it, and you're going to really wish you remembered this substitution because it helps you a lot on some pretty strange homework problems. We know that V is Q divided by A, right? That's the continuity relationship that says for a certain flow rate going through a certain pipe diameter, which gives you a cross-sectional area, you can find the velocity. So this is from Q equals VA. Also, we know that V squared is Q squared divided by A squared. This is going to be a very useful substitution later on. And so put a little star or something next to the slide, because this substitution of FL Q squared divided by D2G A squared, that's the head loss. This will be a very powerful, we'll just use this formula sometimes, and it'll allow us to do things that this wouldn't. Okay, but we're going to take it further for now. What we'll do is we'll say we can rearrange that with the substitution of what is cross-sectional area, FLQ squared divided by D2G, and then substitute in pi d squared divided by 4 squared. So I'm just substituting in what's the definition of A. And that turns into 16 FLQ squared divided by d to the 5th 2g pi squared. Okay. And then if we combine terms and divide things out, that turns into 8 FLQ squared divided by d to the 5th g pi squared. So if we want to know, we want to solve for d, then we say d is 8 FL Q squared divided by h sub f g and pi squared to the 1/5 power. And this is the equation we'll use to design a pipe size. How big should the pipe be? It should be this big, depending on the length of the pipe, the roughness, the flow rate that needs to go through the pipe, the head loss that there is to drive the water from one place to another. If you've got a small head loss, then you're going to need a bigger pipe. But if you've got your origin tank really, really high in the air, which means you've got plenty of head loss to work with, then your pipe diameter won't need to be as big to deliver the same flow rate of water to the destination. Any questions about these expressions over here on the left? All right. So here's the process. This is what you do to apply the equation. And this is an implicit and iterative approach that we're going to have to apply. What we'll do to find out how big the pipe is needed, the problem is that the F value, here's the tricky thing. The F value depends on what? What are some of the, we've just solved the Jain equation, for example. What does the F value depend on? The Reynolds number. Okay? But the problem is we don't know, and the Reynolds number depends on the velocity. But we don't know what the velocity of the water through the pipe is until we know the diameter. But we don't know the diameter until we know the velocity. But we don't know the velocity until we know the diameter. But we don't know the diameter until we know the velocity. So you see, I could say that a few more times just to make my point. But in the example we're going to work, we're going to have to go back and forth 4 times with guess, starting with a guess, and then honing in a little bit more on the final answer on what is the velocity of the water going through that pipe. Because this expression says, well, the pipe size that you need depends on how rough the pipe is, but the roughness we don't know until we know the velocity of water that's going through there. I've just already explained that, so I won't beat on that horse anymore. So we'll start with some guess, because we don't have any idea what the actual F value is at the beginning.
How would you not know velocity if you have G?
We know the flow rate, but we don't know the diameter of the pipe.
Oh,
Yeah, exactly. Yeah. I'm glad you asked that, because probably a lot of people were thinking, we do know the Q, we know the flow rate, and that has units of cubic meters per second. But the diameter, we don't know the diameter, and so that also means we don't know the cross-sectional area. And V, which is Q over A, we know the Q part, but we don't know the area because we don't know the diameter. And since we don't know any of that, we can't know the Reynolds number, which means we can't know the F value. And this diameter required depends on the F value. So our way around that is, let's just cut the Gordian knot, so to speak. We'll pick an F value, just assume a guess, and then find out, well, what would be the diameter if you had that F value, that guess? And you'll say, all right, well, what would be the Reynolds number if that was my guess diameter? And you'll find, well, what's the relative roughness based on that guess? And then you'll say, all right, well, if all of those things are true based on my guess, then what should be the F value based on the Jain equation? You find out what's the answer to everything, and then you'll find out what's the F value that depends on that, and you'll say, well, my guess and this updated F value don't match up right, so I'm going to go through the whole process again with my new F value, because it's a little bit better than my original guess was. We'll cycle through that process a couple of times, and then eventually everything converges. The solution will converge, and our assumed F value will be equal to the calculated F value that we have coming out of the process. It'll make a lot more sense once we set this up in Excel. So let's do that. Let's work an example. We've got an example where a pipe length is 40 meters, and we know that the head loss available is 45 meters. We want to get a flow rate of 300 liters per second through there. And so if this is cast iron pipe, what diameter should it be? That's our unknown. We're going to try and find out what diameter pipe is required. So we're going to go to Excel, start a new file for this one, or you can put it in the same sheet, whatever. But we're going to have the Q, cubic meters per second. We're going to have K sub S in terms of meters. We'll have the length of the pipe. We're going to have the gravitational constant. Let me make that a little bit bigger. All right, we're going to have the H sub F, this driving force, the head loss that's forcing the liquid through the channel, and then the kinematic viscosity. Now let's type in all those values. We know from the problem statement it's 0.3 cubic meters per second. The K sub S here, 0.26 millimeters. And so in terms of meters, that would be 0.26 divided by 1,000. Okay, so now we've got that relative roughness, the equivalent sand roughness in terms of meters. The length of the pipe in the problem statement is 40 meters. G we know is 9.81. The H sub F, that is the head loss that's available. And the kinematic viscosity 1E negative 6. All right. So is everybody getting those in, those constants? All right, so the first thing we're going to have, iteration 1, is 1, we want to assume F. Okay, the F value I'm going to assume, it's a pure guess, nothing more, is 0.015. I just pulled that guess out of thin air. Now the formula that I have for D, let me paste over the formula for D. Here it is. I'll just start working in this one. Okay. So 2 would be, what is the diameter based on that guess of F value? Okay. So calculate D based on assumed F. Okay, so D in terms of meters is going to be equal to, and now I have to type in the formula, equals 8 times L. I'm just going to go up here to the location where I've got it. F4 will anchor it, times the flow rate, anchor that, and square it, divided by, I'll times it by F now also. That's here. So times this F. I'm not going to anchor that though, because I'm going to be pasting this formula over and over again. Divided by H sub F, anchor that, times G, times pi squared, pi squared. And then all of that is to the power of 1 divided by 5. All right. So what diameter of pipe would be needed if this was the F value? 0.158 meters would need to be the diameter. Should I leave this formula up for a little while longer? Okay. Well, pause this.
So here's the formula for the diameter, and we find the diameter 0.1582. The next step in this process is that we need to take a look at what are the flow conditions. And so for step 3, determine flow conditions. And specifically what we're after is we're after the flow rate in cubic meters per second. We're going to calculate the cross-sectional area of that pipe and the velocity of the flow going through the pipe if everything is based on that diameter. And then we're also going to compute the Reynolds number if that quantity of flow is going through a pipe of that diameter. Okay, so the flow rate we already know. It's just the original flow rate. I'll anchor that. The cross-sectional area for this particular pipe diameter is going to be pi d squared divided by 4. Okay, so there's our pipe diameter for, there's the area for this pipe diameter. And then the velocity would simply be the flow rate divided by this cross-sectional area. So now we know it's going to be going 15 meters per second if the diameter is that size. So then what would be the Reynolds number for the flow through the pipe under those conditions? It is going to be the velocity times the diameter divided by the typical kinematic viscosity of water, which is 1 times 10 to the negative 6th. So 1e negative 6, which is like, it gives us the 1 times 10 to the minus 6th. So that is the Reynolds number. Of course, I have an error in my formula here. It should be the diameter times the velocity, not the flow rate times the velocity. So let me move in this formula. I'll move this up. Wait for it. Move this reference up here. And now I've got the correct Reynolds number that I'm looking for. I could have, instead of typing that in manually, I could have also just referenced up here where I have the kinematic viscosity. So, same thing. We've got our Reynolds number. Now, in step 4, what I'm going to want to do is find an updated F value for these flow conditions. So, using these flow conditions and assumed D, find F. So remember, our first F was just a total guess, and I'm going to converge on the true F by constantly updating based on what are the implications of this assumption. So I'm going to call this my new F value, and the way that I find that is I'm just going to use the Jain equation. So let me type that in, the Jain equation here. It's equals 1.325 divided by the logarithm of K sub s. Here's my K sub s reference. I'm going to anchor that. Divided by 3.7 divided by D, my most updated D, this one. Now, doing that divided by 3.7 divided by D, that's the same as if I had had a parentheses here and multiplied them together. But it's slightly fewer keystrokes, and so sometimes I'll do that little trick where I'm divided by 3.7 divided by D. So just be aware that that's one of my moves. All right. So now plus 5.74 divided by the Reynolds number, which we just calculated, to the power of 0.9. And then once I close out that, I need to take it to the squared power because of this exponent here. So all of the denominator squared. Okay, so I'll leave that up for a second so you can look at my references. I'm using the K sub s, the diameter, and the Reynolds number. And this is the Jain equation for the F value. So this is basically saying if you've got that diameter and that Reynolds number for this particular material, then what's the F value? You know, what is the roughness? So rather than just being a strict guess, this finally is starting to introduce a little bit of quantitative logic to it. And so I have an updated F value. Let me switch that from scientific to just general notation. Well, all right. So 0.0224, and that's a big difference from my initial guess was what 0.015. It doesn't seem like a big difference, but it's a huge difference in the spectrum of F value possibilities. So am I done? No, I'm not done, because my assumed F and my calculated F are so different. That means they haven't converged yet, and so I need to do another iteration. I have to keep going until my starting F value and my final F value match exactly. And so basically I'm just going to repeat everything. Repeat. Okay, now just to smooth things along, what I can do though is I can copy everything that I've done so far. Hopefully this works. Let's see. All right, I'm going to highlight all of these. Control C is my copy key, or you can do, I don't even know, copy, Control C, okay, and then I'm going to paste it here, Control V, or you can click paste. Alright, only thing I want to do here is I'm going to call it iteration 2. Okay, so instead of just assuming a new F value out of the blue, wouldn't it be smarter if I said, well, let's use this because that got us closer to the truth. So I'll use the previous F value as the input to my second iteration. So there I go. It comes up with a new diameter. Now, those anchored references at the very top, you know, the dollar signs means that it's looking up here regardless of the fact that I copied and pasted that whole iteration. So that's working as it should. The only thing that wasn't anchored was it's going to look for the F value here at my new input guess. Now it's better than a guess now. It's a previously calculated iteration. So I have an updated diameter. Okay, I've got my flow rate, cross-sectional area based on this diameter. The velocity. Seems like I got a problem with my Reynolds number. Oh, I never anchored the cell reference like I should have for viscosity. So let me move this up here, and then I'll anchor it. Okay, so there it is at viscosity. And the way I can anchor it is either type in the dollar signs, or I'm going to press the F4 button. Boom, anchored. All right. All right, so there's my Reynolds number. And this F value is based on the Jain equation. So the question is how close is the input to the output? 0.224, 0.219. I mean, that's a lot closer than our previous guess was, but I'd like it to be identical. So let's do the same thing. It's easy enough to do another iteration, right? I'm not typing in any formulas. I'm just Control C, then Control V. I'll make this be the guess from the last one. It calculates the new diameter. It calculates the cross-sectional area based on that diameter. Tells me what the velocity will be based on it. Updated Reynolds number. And this F value is awfully close now. 0.0220 and 219. I mean, that's close enough that we could probably quit right there, but just because it's easy and fun, let's do one last iteration. Control C. Oh, That was iteration 3, by the way. That's good to keep track of things like that. 3. Alright, so now here will be iteration 4. Control C, Control V. Change that to say 4. And it's already looking at the previous one. I got the spacing right. If I had pasted that a cell below or a cell above, it wouldn't automatically lock into that. But it does. And so here's the input of 0.0220 and the output 0.0220. So that is our correct F value, which means this is the diameter that we want to build that pipe at. So that is the correct diameter that's needed for the given flow rate. So we've gone through this whole process on the spreadsheet, and what we've just done is basically the more accurate technique for finding the pipe diameter required. There's also a slightly less accurate, but at least it's not iterative. You know, if you don't like doing all those steps, then here is an approach that allows you to find the diameter needed for a given flow rate and a specified head loss. It's so-called easy. You can see I put that in quotes because the formula is a little bit complex. It also has a limited range that it applies. It's a pretty, you know, the limits are wide, from 3,000 to 3 times 10 to the 8th is the Reynolds number. You can see the relative roughness ratio that it's valid for. So it's wide range, and typically the results of this equation you'll get within 5% of the iterative approach. And so let's try that same thing again. Let's calculate based on the length of 40 meters, it being cast iron pipe with this known K sub S and the flow rate of 300 liters per second. Go ahead and try and substitute those values into this equation. And pause this recording as you do. You can give a try. Okay, so you unpause the recording. You can't wait to find out if your answer is correct. What you should get is 0.175 meters. And that's pretty close to what we calculated with the iterative approach. The iterative approach, if you remember, was saying that the needed diameter is 0.171. So it's definitely within that 5% limit that it mentioned.